All right, let's look at homework 24, problem 4. So this is actually that power factor correction one that I said was going to be annoying. So apparently it took Dr. Schwanbaum 40 minutes to do it. So my goal is less than 40 minutes. All right. I sincerely think it'll take significantly less time than that. So we have an unknown voltage source, I believe. And I'm going to call this VS. And I'm going to, if I need it, solve for it as a RMS phasor quantity. Then we have some capacitance here, C, which I believe we are trying to find. Some resistance here, R, which for me, R looks like 6 ohms. And then a load here. Where, let's see, this load draws 15.5 kVA. At a power factor of 0.64 lagging. And we are told that the magnitude of our load current is 23.5 amps RMS. And our goal is to determine what value of C will cause the source to operate at a power factor of 0.95 lagging. So PFS is 0.95 lagging, and our frequency of operation F was given to be 60 hertz. Did that summarize all of the information that we were given? Did I miss anything? All right, so let's figure out what the complex power absorbed by load L is, where L is what's being described by the 15.5 kVA being absorbed at a power factor of 0.64 lagging. So based on those two pieces of information, I can figure out what S is. What does the 15.5 kVA represent? The magnitude of the complex power or the apparent power. So I know that SL will be 15.5 kVA, and it will have an angle of the inverse cosine of 0.64. And because it's lagging, this angle will be positive. So could somebody please tell me what that value comes out to be? Because I don't know that I have a calculator. I would like the, well, obviously the magnitude is going to be 15.5. Sure, so just tell me what the angle is going to be. 50.21 degrees, volt amperes. Okay. Anybody have any problem about the level of analysis that was required right there? You are correct, kilovolt amperes. Thank you, Ian. All right, so now I'm going to find the complex power absorbed by my resistor R. So that should be the magnitude of IL squared times 6 ohms. That's it. So what is 23.5 squared times 6? So 3,313.5 with an angle of 0 degrees. Complex power. Volt amperes. So this guy, as it stands right now, would be in volt amperes. So what I'm going to do is I'm going to move my decimal point 3 over and say that this is in kVA. Now I'm going to add these two guys together because I can say that the complex power supplied by my source is simply the complex power absorbed by my load and the complex power absorbed by my resistor added together. Does that make sense? So S sub S will be S sub L plus S sub R, which will be equal to what? So it was 3,313 angle 0 volt amperes, and to make it kilovolt amperes, that's why I got 3.313. So what happens when I add these two guys together? 17.80, 41.99 degrees, kilovolt amperes, right? So before my power factor correction capacitor is put in, my source is absorbing this quantity S sub S. Could you please tell me what that answer is in polar form, because that will be important in a minute. 13.23. kVA. All right, so I'm going to make a note here real quick. This quantity right here, volt. This quantity right here is theta old. How do I find theta new? .95, but yeah, it's 0.95 for me or whatever, yeah. So what's that going to be? .99 degrees, 19, okay? All right, so as a quick aside over here on the right hand side, draw this line straight. Our power factor correction equation is something like P times the, P old times the tangent of theta old minus the tangent, sorry, I didn't write tangent down here. Theta new divided by omega times VRMS squared, where in this case, VRMS is going to be the magnitude of VS squared. So it's the only thing we don't have to throw into that equation. Right, just knowing what VS is, okay? So what I'm going to do here is to make an assumption, okay? And let me explain what that is. So first, let me say, I'm going to make the assumption that IL has a phase angle of 0 degrees. Okay, that assumption will let me figure out what VS is. I need to assume a phase angle for IL, but the angle that I assume isn't actually important, which is why I'm just arbitrarily choosing 0 degrees. All of the other elements are going to push it where it needs to be for us to solve for VS, if that makes sense. So effectively, the results here for the complex power, theta new, theta old, and all that kind of stuff don't depend on what we assumed for theta I. So we're only looking for the magnitude of V. So the angle that we're assuming here actually won't make any difference in our solution, won't change literally anything. But we do need to make a solution because we can't, what I'm getting at here is we can't simply say that Vs will be the magnitude of Vr plus the magnitude of Vs. Doesn't work that way, unfortunately for us, right? So that's why we have to wind up assuming a phase angle for our current here. Because it doesn't take into account the phase angle differences when you add complex numbers together, right? So instead, we have to solve for an actual value of VL and an actual value of VR and add those guys together to get a value for VS, and then we just take the magnitude of that. Does that make sense? So how do we get VL? That's the hard part here, except that it's not really all that hard. So we know that the power absorbed by the load, SL, is VL times IL conjugate, which means VL is SL over IL conjugate. And because I chose a phase angle of 0, IL conjugate and IL are the same thing. So that's literally just going to be that 15.5 angle 50.21 degrees kVA divided by 23.5 amps RMS gives me a number. Somebody please tell me what it is. It's going to be something with an angle of 50.21 degrees. .660 would be kilovolts RMS. So let's call it 660 point. What are the next three decimal places?
Well, it would be 659.
659.57 volts RMS. What is, sorry, VR? Yeah, 23.5 times 6. Sorry, what was that? 141 exactly? So VS is just VR plus VL. All right. And so this guy right here is the magnitude of VS. We have all the parts to just throw in our generic equation now. 21 minutes. So, like I said, that equation is a fantastic thing. You just have to know how to get the different parts of it. So we did it. Did any of the analysis that we did not make sense? Wonderful. If it made sense, then you're going to do well on the exam.
Omega would be 2 pi over 3, correct?
2 pi times the frequency. Omega is 2 pi f. Mhm. 120 pi, exactly right. All right, what do you guys want to talk about next? We got an hour and a half. Pardon? You will get one. So let me pull it up in my email. So I'll show it to you and then I'll post it as well so that I don't forget. So you have an idea of what it is. I'm gonna disconnect this real quick so you don't see how many the horrifying number of unread emails I have in my thing. Yes, ma'am. Give me just a moment, please. Is it about to be a punk again? Oh, wait, no, it's working. Is it? Okay. So Skylar, up here, we were told that our linear frequency is 60 hertz. Omega is just 2 pi times f. All right. Dang it, I told it to open the equation sheet in Word. Where is it at? Open with Word. There we go. Crap, that's not what I wanted to do. So this is the equation sheet that you will be able to use on your exam. So it includes omega is equal to 2 pi times f right there at the very top so that you don't forget it. Gives you the impedance of inductors and capacitors, but not resistors because that's just R. So hopefully you all can remember that. It has an equation that will allow you to calculate the effective value, tells you what the RMS voltage is for a sinusoidal waveform. Gives you the equation for the instantaneous power, but just tells you that it's literally, so actually this says I as a function of omega t, that should be Im cosine omega t plus b or whatever. And then it gives you the trig identities that you would have to use to calculate the instantaneous power and all that kind of stuff. Let's see, then definition of average power, and then a different definition of average power. Power factor. I think technically this guy right here, I'm not sure what Dr. Cronk is meaning by this one where it's VRMS squared over Z is equal to IRMS squared times Z. Because if he actually means the complex power, the voltage equation should have Z conjugate in the denominator. But yeah, not entirely sure what he means by that one. We have average power given literally yet again, for whatever reason. And then this is your power triangle relationship. Complex power is equal to average power plus reactive power in rectangular form, and apparent power angle, power factor angle in polar form. And then average power, reactive power, complex power, Ohm's law. A third way to calculate the average power. A way to calculate the reactive power based on the reactance of the element, which we barely talked about. Reactance is the imaginary portion of the impedance. The power factor angle can be found by taking the arctangent of the reactive power over the average power, which is definitely true, but not a way that we talked about it in class. You would just use the inverse, the cosine of the power factor angle. And then the equation for determining the capacitance for a power factor correction problem. So there are small little errors here, or just ways that we did things slightly differently. I'm too lazy to update it. Just telling you straight up. This is what you are being provided by the other professors. That is, I acquiesce to that. I will give it to you. I will upload it online so that you can look at it and all that kind of stuff and try to use it as you review and notice which things are maybe need a little bit tweaking or whatever, so that you can make a mental note of that when you do it on your exam. I'm not going to change it because I'm too lazy to do it. Okay. So I am saving it to my desktop. No, I'm not going to save it to my desktop. Ignore the fact that I name my file folders with curse words in them. You didn't see that. I'll have to figure out how to blur things when I upload this video. Let me put it here. Let me go to Moodle. This is circuits 1. Exam review materials. Dropbox. $221. All right, so it has been uploaded into the review materials section of Moodle so that you can have access to it to use it while you study and all that kind of crap over the weekend, etc. Okay, so you have all witnessed me doing it. It is literally on video, so I have fulfilled my obligations with regards to you having access to the equation sheet. Is the matter settled? Okay. What do you want to talk about next?
Problem made by Satan, number 18 on practice.
Okay. Not sure how I feel about being called Satan, but that's all right. Let's see. So that would be in 221, old tests.
That one.
Problem number 18. All right. Do I get to look at my old solution to see what the hell I did the first time?
No, sir.
All right, well then. Oh, this is easy.
Well, I mean, you haven't seen the problem.
It's easy. Yeah, So super mesh 3.5. All right. So let's see. Where is? All right. Boy, okay. So let me. I would like to apologize. I should not say that things are easy and all that kind of good stuff, because if you're struggling with it, it's obviously not easy, and I don't want you to feel bad for not knowing it. So I am sorry for being an ass. Okay. So super mesh 3.5 would be, I don't want to do it in black. Let me make that line a little bit thicker. Yes, sir. So if I start, and I drew right over whether this is the, okay, I'm going to make this to where I can see the positive polarity terminal and the negative polarity terminal, because that will be helpful. So if I start here and follow this path around its clockwise loop, I would have 7 volts. And then this bit right here is a short circuit, so I see nothing. This bit right here is a short circuit, so I see nothing. So the next thing I see is the 36 ohm resistor, and it will have a current of I5 minus I8 flowing through it. Then the next thing will be the 20 ohm resistor, and that will have a current of I5 minus I6 flowing through it. Then I go through this bit, which is just a short circuit. Then I see the 21 ohm resistor, and that has a current of I5 minus I2 flowing through it. Yeah, so for these problems, this is what there were problems like this on the practice exams for exam 1 and exam 2 as well. These are what I call big ugly nodal and big ugly mesh problems. And I used to give these a lot, never with the intention of you actually solving anything, just with you, with the intention of you being able to correctly do the Kirchhoff's voltage law analysis or Kirchhoff's current law analysis, or, you know, kind of relate things or whatever. But because the number of problems on the exam had to decrease so that you could complete them in 2 hours, I stopped giving this type of problem this year. So that is how you would do it. Nothing like that will show up on your exam. Yeah. What's next? Christy. Okay. So let's see. So a steady state sinusoidal circuit that requires us doing some math. That's just combination, so that's not going to be anything important. Okay. So like, I mean, this is the type of problem that I will ask you. So the first thing that we would want to do with a circuit like this would be to take it out of the time domain and put it into the frequency domain. So how would I change this to white and make it really thick? So the first thing I'm going to do is replace this current source IS of t with its phasor equivalent. So what should that be? If IS of t is 3 cosine 3t plus 10 degrees, which is given right here, what's the frequency domain representation of that current? 3 angle 10. Let's do the same thing for the source on the other side, right? This voltage source. So if Vs is 12 sine 3t volts, what would the phasor domain or frequency domain representation be? 12 angle negative 90 degrees. Wonderful job on catching that I put a sine there, not a cosine, so that you needed to do a conversion. All right, so the resistor is obviously just going to continue to be a 3 ohm resistor. What I'm going to do real quick here. So this is Vx of t. So now we're going to convert it to a phasor quantity. X with a bar over it. Similarly, we're going to replace Iy of t with a phasor current. So the last two things that I need to convert are my inductor and my capacitor. So what should my 4 Henry inductor look like? Yeah, so J12, right? 4 times omega, which is 3. So J12. And what about my capacitor? So I have, so it was 1/8 of a farad, right? So 3/8 of a farad. Or excuse me, so I'll have 1 over 3/8, which is 8/3, and then there'll be a negative sign output. So negative J 8/3 of an ohm, if I did that mental math correctly. If I didn't, by all means, tell me what it's supposed to be. But I feel reasonably strongly that I did it right. So I have 3 times 1/8, which is 3/8 in my denominator. So when I take that up to the numerator, it looks like 8/3. So that's why I get negative J 8/3. All right, so for this particular circuit, I would actually do nodal analysis with air quotes. Right? So if I called this guy ground, this voltage right here is also Vx, because Vx is simply the drop over my inductor. And so I could apply Kirchhoff's current law, meaning I would need to know this current, and this current. I actually did give myself a little bit of room here. All right, so Christy, help me out. What's the current flowing to the left going to be? So negative 3 angle 10 degrees amps. All right. Yes, so if you combine the impedances together, it's going to look like Vx minus 12 angle negative 90 degrees volts divided by 3 minus J 8/3 of an ohm is equal to 0. And we have one equation, one unknown, solve for Vx. And that will tell you how to answer number 31. And then now that you know this voltage here, Vx, and this voltage here, the difference in those two voltages divided by the impedance seen here gives you Iy. That is the current flowing to the right through the negative J 8/3 ohm capacitor in series with a 3 ohm resistor. So we combine those two impedances together to effectively eliminate this node here in the middle so that we could set up a system, if you will, that only has one unknown quantity, Vx. We did this on that one day when I worked that same problem like 5 different ways or whatever. That was another way that we could have approached that, right? A potentially different way that you could approach this problem would be to do a source transformation on the practical current source on the left-hand side, and then just figure out what the current is flowing in that single loop, which would be IY or negative IY, depending on what direction you define that current to be. And then once you know IY first, you could write a Kirchhoff's voltage law equation to figure out what Vx is. So always multiple different ways. So this level of difficulty is what you should expect on your exam. Yes.
For the source transformation, you just treat the inductor with the.
So you'll treat the inductor as its impedance, right? So to do that source transformation, that would be 3 angle 10 amps multiplied by J12, which would be 36 angle 100 degrees volts. And that would be in series with the J12 ohm inductor. What do you want to talk about next? So why it's there? Sure. It's actually not going to require a whole heck of a lot of derivation, but I'll be happy to do it. So let me scroll to this next page. All right. So for a generic impedance Z, which has an RMS phasor voltage V, RMS phasor voltage V over it, and an RMS phasor current I flowing through it. I have told you guys that the complex power S is V phasor or RMS phasor times I RMS phasor conjugate. And this looks like VRMS with an angle of theta V multiplied by IRMS with an angle of negative theta I, right? Which would give us VRMS IRMS with an angle of theta V minus theta I. Theta V minus theta I is the angle of Z. So if I don't do the conjugate, I'm not interpreting my impedance correctly. Right. So if I don't do the conjugate, I'll wind up with theta V plus theta I, which is not the angle of my impedance. That's where it comes from. That's it. Yes, ma'am. If we want the absorbed complex power, then yes. So the complex power also obeys the passive sign convention. So when the current is flowing into the positive polarity terminal, we are absorbing complex power. And if the current is flowing into the negative polarity terminal, we're supplying complex power. Mm-hmm. So for sources, typically speaking, we've determined that the power factor at which it supplies power. And for loads, we determine the power factor at which they absorb power. I always specify that on the exam. The reason why we do it that way is if we find the power factor of a source, it's very likely going to be a negative quantity. That's okay. It just means it's supplying power. So the power factor, because cosine ranges from +1 all the way down to -1, it's perfectly okay to have a negative power factor. That just means it's supplying power. But when we do it from the source perspective and saying, find it at which it's supplying power, we're always going to wind up getting a positive number. So I won't give you anything, at least intentionally, where you'll have a negative power factor in circuits 1. Alan. Sure. All right, which direction should I be scrolling? Probably this way, right? Yes. All right, so would you care to work this one? Or have an explanation? Okay, so what are our order of operations for solving an op-amp circuit? Okay, so we have just a couple of steps, right? Number 1 was apply rule number 1 and determine V plus, where rule number 1 was the one that says no current can flow into or out of the input terminals. So if I apply rule number 1, that means that this current has to be 0 amps and this has to be 0 amps. The voltage that I'm trying to find is this guy right here with respect to ground, which is the same as the voltage drop over this 9.1K resistor. So V plus in this case would be 8 volts multiplied by 9.1 kiloohms divided by 3.9 kiloohms plus 9.1 kiloohms, because I have a voltage divider circuit applied at my non-inverting terminal. Step number 2 says that we apply rule number 2 and perform ACL at our inverting input terminal. So that means that this voltage right here is also V plus, because rule number 2 says that there is no potential difference across the op-amp's input terminals, which means whatever we found to be V plus is the exact same thing as the voltage V minus, the voltage present at the inverting input terminal. So if we apply KCL, we are going to have -2 milliamps plus the numerical value for V plus, which we know from the previous step, minus V out over 6.2 kiloohms plus V plus divided by 4.3 kiloohms is equal to 0. Step 3. Just to solve that KCL equation for V out. We're done. Doesn't matter how ugly or nasty I make this look. Those are the 3 steps. So I absolutely understand why you might say that that's a terrifying looking circuit, but if you know what you're doing, it's as trivial as anything else we've covered. Did I make a mistake? I mean, it's possible, but yeah. Okay. I mean, you can, did I work it differently in the solutions or something?
So how do you know that all that the layouts goes down into P plus instead of like some of it going? Are you saying no current goes over the 6.6?
Not at all. I am doing Kirchhoff's current law at that node. So I'm saying this current plus this current plus this current equals 0. I applied KCL in this circuit like I would apply it in literally any other circuit, with the constraint that we know that no current can flow into or out of the input terminals of the op amp. Benjamin.
Have we done anything combining op amps with complex power in this class?
No.
I can't sure it is.
Yeah, I mean, I could give you a circuit that used impedances as opposed to resistances, and it would behave in literally the exact same way, but I'm not going to. Yes, Kobe.
Can you do something with power factor?
Power factor what?
Just one of the questions that has to do with power factor.
So let's look at this guy right here. Number 34 tells us or asks us to determine the power factor at which the source is supplying power. Okay. So we have this big ugly circuit, and we are told what VS is. So that is useful. So I am going to define I'm trying to think about how I want to approach this because there's a couple of different ways that I can do it. Okay. One way is to find what this current IS is. And when I know VS and IS, I can then determine the complex power supplied by the source. And then whatever angle I get is my power factor angle, and I can calculate it that way. Another way that I could potentially do it is say that the power factor at which the source operates has to be the same at which, or the power factor at which the source supplies power has to be the same as the power factor at which all of those loads together combined absorbs power. So effectively, it's which perspective do I want to look at this guy? Okay. So let's say let's do it the way that I've indicated on the screen here. What would be, I don't want to say the easiest way, but a way for us to figure out what that current IS is? Yeah, inductor impedance combination, right? So effectively, this voltage source on the left-hand side doesn't care that it's 4 different things. We can combine them all together and treat it as a single equivalent impedance, where that equivalent impedance would be ZA in parallel with ZB in parallel with ZC in series with ZD. I don't have a calculator on my person, so I can't, do the math right there, but that's literally all you would need to do. Then IS would simply be VS over ZEQ. Then you would say that S is equal to VS times IS conjugate, which will give you your complex power in polar form. That would be the apparent power and the power factor angle, and the cosine of the power factor angle is your power factor. what would you all care to talk about next? We still got about an hour left.
That was basically something with the concept. It's just like a simple problem, just as imaginary numbers.
Yeah. That's all this crap is.
Want to do all the web work?
All of them, not particularly. I'm happy to target my attention to specific problems. So, I mean, if you tell me I'd like help on problem blah, blah, we'll work it. But just say, do all my homework, I'm less than enthused about.
Well, let's move to question one, not because I want to work on my homework.
Okay, so homework 24, question 1. All right, I feel like this probably timed out on me. Yep. All right, homework 24, problem 1. Okay. So I have a voltage source V1, and I want to be clear about this. If we look at the problem, the units on V1 are volts, which means we are given a phasor voltage and not an RMS phasor voltage. The reason why that is important is because we are determining complex power for all of the parts of the problem, which means we're supposed to be working with an RMS phasor voltage. So I'm going to fix that by calling this voltage V1 over the square root of 2 will be V1 as an RMS phasor. Then I have, let's see, a 6 ohm resistor. And an inductor that is J4. It doesn't tell me that it's resistors and inductors, but I can infer that from the impedance. Then I have my minus J10 ohm capacitor. Five ohm inductor. And probably a voltage source over here as well. So this would be V2 over square root of 2, which I will call V2 RMS phasor. All right, so we're going to work this problem almost identically to the problem that Christy asked about earlier. I'm going to call this bottom node here my ground. And I'm going to call this voltage here V minus J10. And so I could say that V minus J10 minus V1 divided by 6 plus J4 ohms plus V minus J10 over minus J10 ohms plus V minus J10 minus V2 divided by 5 ohms is equal to 0. And that's enough information for me to solve for V minus J10. Once I know that voltage V minus J10, S minus J10 is just the magnitude of V minus J10 squared divided by positive J10 ohms, because it should be the conjugate of the impedance. So that's like 1/5 or 6 of the problem taken care of already. Okay. So I'm going to call this current right here I 6 plus J4, where I 6 plus J4 is simply V1 minus V to the minus J10, or V minus J10 divided by 6 plus J4 ohms. And I can then say that the complex power absorbed by my 6 ohm resistor, which I'll call S6, is going to be the magnitude of I 6 plus J4 squared times 6 ohms, and SJ4, the complex power absorbed by the inductor, is going to be the magnitude of I 6 plus J4 squared times J4 ohms. So now I've got 3 of the problems taken care of. Am I asked to find the complex power absorbed by my sources? All right, so let's take care of that one too while we're at it. So obviously, the power absorbed by my sources. Well, actually, no, hold on. We'll come back to the sources in a minute. We'll do that next. So let's call this guy I5. I5 is just V minus J10 minus V2 over 5 ohms, which means that S5 is I magnitude of I5 squared times 5 ohms. Since that current I5 flows into the positive polarity terminal of our right-hand current source, SV2 is equal to V2 times the conjugate of I5. And circling back around, I6 plus J4 is the current that flows into the negative polarity terminal of my voltage source V1. So SV1 is equal to V1 times negative I6 plus J4. I'm done.
Doesn't matter if the negative inside of the conjugate.
It should be inside of the conjugate. I don't know that it matters, actually. So what the negative sign is going to do is going to change the sign on the real part and the imaginary part, and then you just change the sign back on the imaginary part from the conjugate operation. So I don't think it would actually matter if you conjugated it first and then made it negative.
If you calculate it without the negative, you just have power supply.
Yeah.
Put the negative again.
Yeah.
Thank you very much.
Yeah, so that's problem 1 in, I don't know, 4 or 5 minutes. Obviously, we didn't do any of the actual math involved, but the circuit theory is all there. What's next?
Do you think we could like briefly go back over like since we started like imaginary stuff, I kind of got lost with all like the terms like phasors and then time frequency domain and all that. I just want to get like
Absolutely. Absolutely. Let me see. I'm on page 12 here for some reason, so let me find some blank space. All right, so vocabulary review. That's actually pretty reasonable request because this stuff can be confusing. All right. So in the time domain, actually, let me put that up here. So in the time domain, our voltage signals will be of the form Vm cosine omega t plus theta v volts, and I of t will be, our currents will be of the form Im cosine omega t plus theta I. Okay? We pretty much only use the time domain to calculate our instantaneous power P of t. That's pretty much it. And you don't even have to do it in the time domain technically. Okay. Then we have our frequency domain. That just looks like the hottest garbage of me trying to spell. And I often refer to this as the phasor domain. Those two terms are interchangeable. So in the phasor or frequency domain, we represent our time domain quantity by a complex number, but we use a very specific shorthand notation. So our complex representation will simply be magnitude with an angle of theta v for our voltages, and our current will simply be the magnitude of our current angle theta I. This is where let me say this. S right. SSS, or steady state sinusoidal circuit analysis. Our last change is the RMS frequency domain, where V with a squiggle over it instead of a bar over it is simply V with a bar over it divided by square root of 2, or Vm over root 2 with an angle of theta V, which is the same as VRMS angle theta V. And our currents will follow suit. The RMS frequency domain is where we do all of our complex power those are our definitions.
We have complex power, the apparent power and reactive power are the real and imaginary parts.
Right.
Rectangular.
So apparent power, yeah. So I'm just going to draw a quick power triangle here. This is the real axis. This is the imaginary axis. Here is a generic complex power S. The projection of S onto the real axis is the average power. The projection of S onto the imaginary axis is the reactive power. The length of S is the apparent power. And then this guy right here is our power factor angle. So complex power S is equal to V RMS phasor times I RMS phasor conjugate is equal to P, which is average power, plus JQ, which is reactive power in rectangular form, or the magnitude of S, apparent power, angle, theta S, power factor, angle. The units of average power are watts. The units of reactive power are volt amperes reactive. And the units of apparent power and complex power are volt amperes.
Identical, but
Yes, they are all dimensionally identical, meaning that they are VRMS times IRMS, but we use the different terms to let us know which portion of the complex power we're talking about at any given time. So it's a bookkeeping kind of thing versus any real thing. Kobe. Because S is a complex number. So it's not in the, since it's a power, it's not particularly in the RMS phasor domain or the frequency domain. It's actually both of them because it doesn't matter. Like we could use V bar and I bar if we just put a factor of 1/2 in front, and we get literally the exact same results.
That's where that average power equation comes from.
Mhm.
the VMI and the other two.
Yep.
Understand.
Yeah. Pardon? Always. It's just whether or not the imaginary part is 0. So a DC circuit can absorb complex power. It's just going to be all real. So resistances absorb reactive power. Inductors absorb, excuse me, what did I just say? No. Resistances absorb average power. I'm sorry. Resistances absorb average power. Inductances absorb reactive power. Capacitances supply reactive power. Sources supply whatever type of power they need to make the circuit work. They are in, since they're power, they can be in the RMS phasor domain or the phasor domain. So when you're calculating those quantities, V and I should be in the RMS phasor domain. If you don't want to have to remember to carry a factor of 1/2 and all that kind of crap around, which I don't like to do. So the RMS frequency domain lets you use your DC relationships because it's using those effective values, which is the DC representation of that AC signal. So you get to throw away that pesky factor 1/2 that kept popping up all over the place because we were multiplying cosine functions together. No, so the computation of complex power is V times I conjugate, and then you can break it down into its constituent parts. So the rectangular form contains the average power and the reactive power. The polar form contains the apparent power and also tells you what your power factor angle is. Now, that being said, for a generic impedance, Z, having a phasor voltage V over it, or RMS phasor voltage V over it, and an RMS phasor current I flowing through it. S is V times I conjugate, or these are going to be identical representations. The magnitude of V squared divided by Z conjugate, or the magnitude of the current squared multiplied by Z. You can't use those on sources because you don't have an impedance for the source, but you can use those for resistors, capacitors, inductors, or any combination thereof, and those will work. I'm giving you those so that you only need to know the voltage drop over the impedance or only the current flowing through the impedance so that you don't have to bother with calculating both quantities because that takes time. Pardon? Conjugate. Uh-huh. So if you want the magnitude of a complex number, it doesn't matter if it's in the frequency domain or the RMS frequency domain, it's the part that isn't the angle. That's it. So I tried to encapsulate that here, right? So if we look on the right-hand side where it says the RMS frequency domain and the very right-hand representation, what I have written there, VRMS, is the magnitude of the RMS phasor. And then theta V is the phase angle of the RMS phasor. When we look in the middle at the frequency domain, VM is the magnitude of the phasor, and theta V is the phase angle of the phasor. Yeah, and the RMS bit there also is telling you it's a magnitude. So it's just the magnitude is the magnitude of the complex number, and the phase angle is the phase angle of the complex number if you're using a polar form representation, right? So I pretty much never do voltages and currents in rectangular form because they don't contain the information that I need to do any analysis easily. What's next? Yes, sir. Number 9 on the practice exam. Sure. All right. B. So, okay, so you want a reason why, I guess then. Okay. So if we look at A, that's just a resistor. So a resistor operates at a power factor of 1 because all of the power absorbed is average power. So the power factor ratio there would be 1, right? 1 is neither leading nor lagging, okay? When we look at C, the power factor angle is going to be negative 90 degrees, which means the power factor is 0. 0 is neither leading nor lagging. If we look at E with just the inductor by itself, the power factor angle will be positive 90 degrees, which will mean the power factor is 0 as well, which is neither leading nor lagging. So the ones that we need to concern ourselves with then are B, D, and F, okay? Because they're the ones that are actually going to fall somewhere between 0 and 90 degrees, or 0 and negative 90 degrees. The capacitor ones are going to have a leading power factor because there's a capacitor there. The inductor is the one that's going to have a lagging power factor. So anytime we have an inductive load, and by that I mean the real part is positive. Actually, I take that back. The real part is non-zero, and the reactive part is positive, meaning there's an inductor present. will have a lagging power factor. Anytime the real part is non-zero and there's a capacitor present, we'll have a leading power factor. And you could get all of that just by looking at, if you calculated the impedance of that guy and looked at its phase angle, you would see that the phase angle for B will always be positive. The phase angles for D and F will always be negative. Theta V minus theta I. So in a capacitor, we've proven this at least 3 different times in this class, but in a capacitor, the current leads the voltage by 90 degrees, which means the phase angle of the impedance will be exactly negative 90 degrees. So the impedance of a capacitor is negative J divided by omega C. That negative J is the negative 90 degrees phase angle. Just like for an inductor, the impedance is J omega times L, but positive J is the positive 90 degrees phase angle of the impedance. So anytime you have resistance coupled with an inductance, it doesn't matter if they're in parallel or in series, you'll always wind up having a lagging power factor. And anytime you have a capacitor connected to a resistor, it doesn't matter whether or not they're in parallel or series, you'll still wind up having a leading power factor. Yeah, no, it definitely does. It's tricky to remember those things. Yeah. Hey, there's a handy mnemonic device to do that, actually. I can't believe I didn't teach you guys this earlier. So, mnemonic. No, there is a mnemonic device. All right, so where's this thing? I can't believe I didn't talk about this earlier. Maybe I did, and I forgot. Eli the Iceman. E-L-I-I-C-E. Okay. So E is electromotive force, which is the same thing as voltage, and I is current. So in an inductor, which is what L is for, the current lags the voltage because it comes later on. For a capacitor, the voltage lags the current because it shows up later in ice. So Eli the Iceman tells you exactly what you need to know about leading and lagging for capacitors and inductors. Cannot believe I forgot to talk to you guys about this earlier. Pardon? Okay. Yeah. I had never heard of it until I was actually teaching this class, and an Indian friend of mine was like, "Oh, why don't you teach them this?" And I was like, "What the hell's Eli the Iceman?" And then she told me it, and I was like, "Oh, that's actually pretty damn smart." All right, what's next? $25 and $26. All right. Pardon? Oh yeah, totally accumulative then. There is absolutely a transient analysis problem on your test. All right, so something to remember, and I say remember because it sure shit isn't on your equation sheet, is the generic equation for transient analysis, right? Which says that y of t is y at 0 minus for t less than 0 minus, and it is y at 0 plus minus y at infinity, e to the minus t over tau plus y at infinity for t greater than or equal 0 plus. That is the generic equation. I literally ask you the question in the correct order that you're supposed to use to solve for all of the different constituent parts and all of that kind of good stuff. So for example here, looking at number 23, right? In the circuit above, the switch has been closed for a very long time before opening at t is equal to 0. The value of VC of t at t is equal to 0 minus. So that's before the switch opened up. So we would treat the switch as a short circuit. We would treat the capacitor as an open circuit and figure out what that voltage is. And I would argue that we could do it using, sure, that'll work. I was going to say maybe it's, yeah. I mean, you can do it any way that you want to. I'm just trying to think here. If I would do voltage division or not, maybe. Any way you feel like solving for it will work, okay? For number 24, we're asked to figure out what the circuit is doing at t is equal to 0 plus. So at t is equal to 0 plus, our switch is open. Why is this not erasing? Well, this is just making it worse and worse and worse. Okay. Well, that switch is supposed to be open, and you replace the capacitor with a voltage source, having the value of the voltage at V was equal to 0 minus, because the voltage drop across the capacitor cannot change abruptly, right? So whatever value it had at t is equal to 0 minus, it needs to continue having at t is equal to 0 plus, and then you analyze your circuit. The next problem would ask you to analyze the circuit at t is equal to infinity. And so at t is equal to infinity, the switch is still open, but now the capacitor looks like an open circuit again, because you've gone back to a DC steady state condition. Then the fourth part of the problem asks you to determine the time constant for the circuit. So you take the capacitor out and look in during the transient condition to see what resistance the capacitor sees. And then finally, the last part of the problem tells you put crap into the generic equation and math, math, math. I mean, I'm not going into a whole bunch of detail because I think I have 3 videos and a different review that we did. We beat this to death. Drew. Absolutely. What was the question? Yeah. So capacitance describes how things change with respect to an electric field, and inductance is how they change with magnetic fields. And we covered that when we did the theory behind why capacitors behave like capacitors and why inductors have their, yeah. So magnetic fields are associated with inductors. Electric fields are associated with capacitors. As a shorthand way to remember what the answer is supposed to be. No, just paying attention in my class and your physics 202 class. Yeah, that'll work too. So an inductor stores energy in its magnetic field, or the magnetic flux compressed inside the coil. Capacitors store energy in the electric field that's present between the plates. Jacob.
How much is this solved using analysis?
60% or less. The reason why I say 60% or less is because 40% of the exam will be the complex power relationships where if you're setting up a system of equations, you're doing it wrong because your calculator can't handle it. So 60% or less. Yeah, so that the concept questions would be in that 60%. I guess technically you can't do any of those either. So, gosh, so it's 12 out of the 25 questions. Yeah. I guess technically have the capability in some way, shape, or form, potentially, of being able to use mesh analysis. Yeah, sounds like a terrible, terrible plan. No, I don't know why you would need one, but no.
Yeah, we just got our circuit placed in. Every waveform to the exam.
I feel like doing the math would be way shorter than you guys trying to figure out how to set up circuits.
That's a little rude, if not incorrect.
All right, what's next? All right. Study up over the weekend. If you have any more questions, show up on Monday and ask them.